In this lesson, I'm going to start off by talking about the relationship between a rational exponent and a radical. And then we're going to go ahead and do our first example. So first of all, if I look at this radical, notice it's taking the square root of 9. And if I were to put that in my calculator by hitting second and x squared to get my radical symbol, and I were to put a 9 in it and hit equals, notice it gives me 3. So the square root of 9 is equal to 3. Now there's a few components here, and one of them is invisible. Anytime you've been given a square root, what you're really being told is you're being asked what number times itself gives you the number that's inside of the radical. And I want to talk a little bit about that idea. In other words, since 3 is the answer, we could also say that 3 times 3, or 3 squared, is simply equal to 9. To undo the squaring, if we want to figure out what number multiplied to itself to give us 9, we take the square root of it, and it takes us back to our base. The base being this value that doesn't have the exponent. So notice our answer, what we call the square root, is also our base. Now with that being said, I want to kind of point out the components of this radical. So this radical, first of all, it has what we call an index. Now it's always implied and it's invisible, but there is always an invisible 2 on every radical here, just like we have an exponent of 2. And so this particular number 2 that's right here, we call that the index. And you're going to be using that index today with some of the problems you're going to be doing. The number that is inside of the radical, right here, in this case, that number 9, we call that the radicand. And the exponent of the value of the radicand, I'm actually going to write a 1 here. Anytime there's a 9, there's also an invisible 1, and that is our actual exponent of that value. And then the symbol that went around it, that you hear me calling a radical, that is just simply a radical. Now I've kind of defined these different parts of this radical that you see, right, and its answer, and now we're going to use that in a little bit different way. So let me give you an example. I told you that here this 9 has an exponent of 1 and it has an index of 2. If I wanted to write this as an exponent, I could actually rewrite this as 9. Now remember I told you that it did have a power of 1 here, and so that power of 1 is going to be part of the new exponent that I write for it. And so I'm going to go ahead and put a fraction bar up here because we're going to write a rational value, or a fraction, for its exponent. And the power is going to be, the numerator I should say, is going to be this exponent value that's inside the radical of 1. And then the denominator is going to be the index. So in other words, I'm going to write an arrow here. The numerator is the exponent, and the denominator is what we know as the index. So this is just a relationship that they have with one another. And just as we found the square root of 9 is equal to 3, if I were to take and rewrite this, and I got 9 to the power of 1/2, if I were to put it in a calculator, it's going to give me the same value. It's also going to be equal to 3. Now this will prove true with every one of these. It doesn't matter what number you use. So I'm going to do 1/2, and notice it gives me 3. This is going to be important because what we're going to be doing is we're going to be taking exponents and converting them to a radical that has an index. Now sometimes the index will be 2, like in this case the denominator is 2, so our index was 2. But sometimes we're going to have some that have an index of 3 or 4 or 5. So I'm going to write one more example just to kind of show you how we could set this up. So I'm going to go over here, and let's say we had, I'm going to say 5, and this time I'm going to give the power, I'm going to say, you know what, let's do 2 for the numerator, and let's do 3 for the denominator. Remember that the top number is our exponent of the radicand, and the bottom number, the denominator, is the index of our radical. So if I wanted to rewrite this, I could rewrite this as, I'm going to put a radical, I'm going to put a 5 in there, And since the numerator is 2, I put a 2 for the power. And since the denominator is 3, I put the 3 for the index. In other words, whether I put 5 to the power of 2 over 3, or I take a cube root of 5 squared, I should get the same answer. And I'm just going to show you in a calculator to prove to you that it's equivalent. So I'm going to go ahead and put 5 to the power of 2 over 3. We have 2.924. Or if we go ahead and hit math and pull up our cube root, and we do 5 squared, we get the same thing, 2.924. Now, with this being said and understanding this relationship, now we can go ahead and we're ready to solve a problem. So let's go to our first example. So on example 1, we have a parenthesis and we have negative 2a, all in parentheses, to the power of 4 over 3. So what we're going to do is we're going to go ahead and we're going to convert this into a radical. And it's going to be a cubed root, and the way I know that is because this bottom value, right, the denominator of my exponent, is my index. And so therefore we call it a cube root because it means it's going to be a number that's multiplying to itself 3 times to give you a specific value. Keep in mind that this value at the top, right, it is our exponent to the radicand. And the radicand will be, it'll include this entire portion right here, the parentheses and the negative 2a. So that's going to be our radicand. So I'm going to go ahead and rewrite this real quick as a radical. And so what I end up with, I'm going to go ahead and put my radical symbol. At the end, I told you my index was 3. So for the index right here, I'm going to put a 3 above that radical. And then I'm going to put my radicand in it. That's going to be parenthesis, negative 2a, close parenthesis. And now we're going to put our power to this radicand, which is our numerator of 4. So from this point, I now need to go ahead and use the power to power rule for the exponents to distribute this power of 4 to the negative 2 and distribute this power of 4 to the positive 8. So let me show you what that looks like. I'm going to go ahead and I'm just going to write this out so you can see every single step. Just this is an example. I want to make sure that you got down what we're doing here so it doesn't look like any magic is occurring. So in other words, this power of 4, the power to power rule says it must be distributed to both the values that are inside of the parentheses. So I have negative 2 to the power of 1 times the power of 4. And then we have a to the power of 1. And if you're wondering, well, Mr. H, how do you know that has a power of 1? Well, it didn't have a power written above each one of these numbers, so I know that the power has to be 1. And it's times the power of 4. Keep in mind that I'm going to put some parentheses around here. And so do keep in mind that I have parentheses right here, right? Because while it doesn't make a difference with the a value, it will make a difference with the negative 2. Because if you fail to recognize that the parentheses are on there and you don't put them on there, and you put it in a calculator, this negative is not going to change to a positive. And so let me show you what I mean by that real quick. I'm just going to give you a demonstration. If I were to say negative 2 to the power of 4, it would give me negative 16. But this is really negative 2 to the power of 4. And notice that gives me a positive 16. So I'm going to go ahead and just continue working this out. Right? If I were to rewrite this in just all little steps, we would have the square root of negative 2, and 1 times 4 gives me 4, so to the power of 4. And that would be times a to the power of 4. Right? And what went on inside the radical right here, this is nothing new, right? This is just your property of an exponent for the power to power rule. Whenever you have a power outside the parentheses, you must distribute it and multiply it to the power of the values on the inside of the parentheses. So I'm going to go ahead and we're going to simplify this a little further. So I'm going to move it up just a little bit. So this actually becomes 16. And with the a, we really can't do anything with it, right? We don't know what the number is. So it's just a to the power of 4. Put my dot there, just showing that we are multiplying those together. Now this is all in a radical that has an index of 3. And that's going to be important because it's going to change how we do some things if you were looking at any of my videos on how we handle a radical with an index of 2. Now the next thing I want to do is I want to do what I call prime factorization. I want to see, can I simplify this 16 right here? And I'm going to write my prime numbers. If you forgot, you can do prime factorization of any radical, and I recommend you use prime numbers. It makes it really simple. And you can use 2, 3, 5, 7, 11, and 13. And these will work for the majority of all radicals that you have to factor. So I'm going to show you what I mean by that. I'm going to break this 16 up. And I don't know what all numbers can go into it that I have right here, but 2 is always the number that I like to start with. And so I'm going to go ahead and do 16 divided by 2. And notice it'll go in 8 times. So I can say my factors of 16 are 2 and 8. I'm going to continue that process until I get a prime number at the very end, and I can't go any further. So let me go ahead and take 8 and divide it by 2, and notice I got 2 and 4. And then I'm going to just continue this factor tree. I'm going to break down 4, so 4 divided by 2, and it gives me 2. Now what's important here is I'm stopping because I'm at a prime number, right? 2 is one of my prime numbers. I have a prime number here on the bottom right, so that tells me that I can stop right there. And I have all my factors of 16. In other words, I have a 2, I have another 2, another 2, and the last 2. Now if you're going, Mr. H, what do you mean by all these 2's? Well, what I mean is, if I wanted to get the square root of 16, I could simply take this 2, multiply it to the next 2, and multiply it to the next 2, and the last one on the bottom right. And it would just take me back to 16. So what I've really done here is I'm going to rewrite this as radicals. Let me move the camera. So I'm going to write this as the square root of 2, and I'm going to cross them out as I do each one. And then times another square root of 2, times another square root of 2, and the last one. So notice I have crossed out all 4 of these, all the ones on the left and the bottom right, 1, 2, 3, 4. And so the square root of 16 is equal to the square root of 2 times the square root of 2 times the square root of 2 times the square root of 2. And why this is beneficial is because we can go ahead and look at our index, and notice I'm going to circle the index. The index was 3. And what that tells me is, for every 3 radicals that are the same value, I can simply convert them to the radicand. In other words, since our index is 3, I'm going to circle 3 of these radicals, these square roots of 2 that are being multiplied together, and they simply become the radicand, which is the number on the inside. In other words, they become 2. Now, the reason that this works is because our index is 3. If the index was 4, well then all 4 of these, I could circle all 4, and they would just become the radicand, which is 2. If the index was 2, well then I would just circle 2 of them, and 2 of them would become 2. So whatever the index is going to tell you how many radicals it takes to become the radicand. Now notice there is one left over, and I'm going to show you what to do with that one left over in just a moment. But before we do that, let's go ahead and deal with this variable. Now the variables are actually easier to deal with than the numbers, than the integers that we deal with. So I'm going to bring that down. The reason I say they're easier is because notice it says a to the power of 4, which means we have the square root of a times the square root of a times the square root of a times the square root of a. So notice I just wrote it 4 times. I didn't have to find factors for it, so that makes it easier in my opinion. Now I do need to group 3 of these a's together, because for every 3 radicals of a, it just becomes a value of a outside of a radical. So now I've been able to eliminate everything except for 1 square root of 2 and 1 square root of a. Because I don't have enough of these radicals in order to cancel out the radical symbol, I'm simply going to rewrite them at the end of my answer. So for instance, square root of 2, I'll put that right here. Notice I am going to extend my radical a little bit because not only am I going to put the 2 in there, but we also have a square root of a that we need to put in there as well. And so we're just putting them back together. And so my final answer for this problem is 2a square root of 2a. And that's my final answer.